Welcome to the session on differentiation, review exercises. The objectives for this session are to review previous topics through exercises, namely, explore examples of differentiating quadratics, explore examples of differentiating functions with two or more terms, use parametric equations to solve problems involving coordinate geometry, and solve equations which involve secant, cosecant, or cotangent. We will now solve the review exercises shown on your screen. Do pause the video and have a go at these. When you are ready to view the solutions, press play. Before solving the first exercise, we're going to take a look at some theory which will help us to solve it. Recall that for all real values of n and for a constant a, if y equals ax to the power n, then dy dx equals an times x to the power n minus 1. A function with more than one term can be differentiated by differentiating terms one at a time. If y equals ax squared plus bx plus c, where a, b and c are real, then dy dx equals 2ax plus b. How do we differentiate multiple terms? If you can rearrange each term of a function so that it is expressed as ax to the power n, then you can differentiate the function one term at a time. In other words, if y equals f of x plus or minus g of x, then dy dx equals f dash of x plus or minus g dash of x, where f dash of x and g dash of x are the differentiated expressions of f of x and g of x, respectively. So here's a summary of the key points. And here's the first exercise. So let's solve example 1a first. We are required to differentiate y equals 2x cubed plus 9x. We're going to do this term by term. If y equals 2x cubed plus 9x, then dy dx equals 2 times 3 times x to the 3 minus 1 plus 9. How did we obtain this? We've simply plugged in the values for a and n for this particular term into our formula. So we obtained for 2x cubed, a equals 2 and n equals 3. And we plug that into dy dx equals an times x to the n minus 1. Similarly for 9x, here we have that a equals 9 and n equals 1. And we've plugged that in to find dy dx for 9x. And then tidying up gives us dy dx equals 6x squared plus 9. Now let's solve example 1b. We are required to differentiate the expression shown on your screen. So if y equals x to the 4 plus x cubed minus 2x to the power a half, then we have dy dx equals the expression that you can see now. So let's break this down term by term. So for the term x to the power 4, we have that a equals 1 and n equals 4. And this gives us the resulting dy dx for this term. For the term x cubed, we have a equals 1 and n equals 3. And hence dy dx equals 3 times x to the 3 minus 1. And finally for the term minus 2x to the power a half, a is equal to minus 2 and n is equal to a half. So we have this slightly complicated expression highlighted in red for dy dx for this term. We can therefore tidy up to obtain dy dx equals 4x cubed plus 3x squared minus x to the power minus a half. Now let's solve example 1c. We are required to differentiate the expression on your screen. Now if y equals 4x to the power a third minus 3x cubed, we have this expression for dy dx. Again, let's break this down term by term. So for the first term, a equals 4 and n equals a third. And for the second term, we have a equals minus 3 and n equals 3 to give this expression for dy dx. And so tidying up gives us that dy dx is equal to 4 thirds x to the power minus 2 thirds minus 9x squared. Now let's solve the next exercise as shown on your screen. So let's solve example 2a first. Let f of x equal 5x squared minus 6x plus 7. Find the gradient of y equals f of x at point 2, 15. So if y equals our given quadratic, then dy dx equals 10x minus 6. Here's our quadratic, and here's dy dx. So each term has been differentiated. And we've simply plugged in the values of a, b, and c into our formula. Now at 215, dy dx equals 10 times x minus 6. And here we have x equals 2. This, of course, gives us 10 times 2 minus 6, which is equal to 14. Now let's solve example 2b. Let f of x equal 5x squared minus 6x plus 7, at which point on the graph is the gradient equal to 5. So let's solve this. Now if y equals our given quadratic, then dy dx equals 10x minus 6. Here's our quadratic, and here's dy dx. Now from our question, we know that the gradient is equal to 5. So therefore, given that dy dx equals 10x minus 6, we can conclude that dy dx equals 10x minus 6 equals 5. If we rearrange this, it gives us that x equals 11 over 10, or 1.1. And then plugging this into our equation for y gives us y equals 6.45. So the gradient is equal to 5 at the point 1.1, 6.45. Now let's solve example 2c. Let f of x equal 5x squared minus 6x plus 7. Find the gradient of the curve at the point where the curve meets the line y equals 4x plus 2. At the point of intersection, we have 5x squared minus 6x plus 7 equals 4x plus 2. So rearranging gives us 5x squared minus 10x plus 5 equals 0. And then dividing by 5, and factorising gives x minus 1 all squared equals 0. So at the point of intersection, x is equal to 1, because this is the only solution for this particular equation. Now we know that dy dx equals 10x minus 6. And therefore the gradient at this point, when x equals 1, is equal to 10x minus 6 equals 10 times 1 minus 6, which of course equals 4. Before moving on to the next exercise, let's remind ourselves of some theory. The x and y coordinates of each point on a curve can be written as functions of a third variable. This variable is usually represented by the letter t and is called a parameter. A curve can be defined by using parametric equations of the form x equals p of t and y equals q of t. Every value of t defines a point on the curve with the coordinates p of t, q of t. Here's the next exercise. Let's take a look at part A first. The diagram on your screen shows a curve C with the parametric equations x equals at squared plus t and y equals a times t cubed plus 1, where t is a real number and a is a non-zero constant. We are required to find the value of a. So let's solve this. Now at the point 1, 0, we have that x equals 1 and y equals 0. And therefore, if we plug into the equations that we have for x and y, we obtain 1 equals at squared plus t and 0 equals a times t cubed plus 1. Therefore, we have that t cubed plus 1 is equal to 0, since a is a non-zero constant, as shown. And therefore we have that t is equal to minus 1. We can now substitute this value into the equation 1 equals at squared plus t. To give us 1 equals a times minus 1 squared plus minus 1. And of course, rearranging this gives us that a equals 2. And now for part B. We are required to find the coordinates of the points A and B where the curve crosses the y-axis. So let's solve this. At points A and B, the x-coordinate is 0. Therefore, if we plug in a equals 2 into the equation x equals at squared plus t with x equal to 0, we obtain 0 equals t times 2t plus 1. And so we have t equals 0 or t equals minus a half. Now at t equals 0, if we plug this in to the equation for y equals 2 times t cubed plus 1, we obtain y equals 2 times 0 cubed plus 1, which is equal to 2. At t equals minus a half, we can plug this in likewise into the equation for y to give us y equals 2 times minus a half cubed plus 1, which is equal to 7 over 4. So at point A, when x equals 0, y is equal to 2. And at point B, when x is equal to 0, y is equal to 7 over 4. Therefore, A equals 0, 2, and B equals 0, 7 over 4. Before moving on to the next exercise, let's remind ourselves of some theory. Recall the reciprocal trigonometric functions. Sec equals 1 over cos, cosec equals 1 over sine, and cot equals 1 over tan. Since tan equals sine over cos, we have that cot equals cos over sine. Let's remind ourselves of the graph of y equals sec x for x in the real numbers. This will look something like this. As you can see, there are no solutions for sec x equals k for k between -1 and 1. Similarly, for the solutions for y equals cosec x. And here's its graph. There are no solutions for cosec x equals k for k between -1 and 1. Let's now take a look at the final exercise and solve. Now sec x equals 2 implies cos x equals 0.5. We've simply replaced sec x by 1 over cos and rearranged the equation. So let's now take a look at cos x equals 0.5. Here's the graph of cos in the given interval. If we draw a line at y equals 0.5 as shown, we can see one solution, at least, at 60 degrees, as indicated. However, the line does cross the graph at another place as well, namely here at minus 60 degrees. Therefore, there are two solutions. Cos 60 degrees equals 0.5 and cos minus 60 degrees equals 0.5. This brings us to the end of this session. If you have understood its contents, you should be able to explore examples of differentiating quadratics, explore examples of differentiating functions with two or more terms, use parametric equations to solve problems involving coordinate geometry, and solve equations which involve secant, cosecant, or cotangent. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.